the official class Mr. Hegseth. Well, yeah. I don't know if you call him a DEI hire, but yeah, what he is chosen to look good. Trump staffs his people like they're for a TV show. So he likes the way Hegseth looked and the fact that he was on TV. That's what it is. He's making a TV show about being president. He's not making an actual administration. Anyway, if you're interested in going to events, they're coming very soon. This weekend is B-Sides. Some students I know are volunteering there. Hack the Bay comes after that, which is a very good event. I'll be at this one. And then RSA comes all next week. So you can go to the expo all day if you Google and find an expo pass. And if you sign up in advance, you can go to free Thursday College Day. That's when I'll be there. So I highly recommend doing these. And if you do any of them, it's worth extra credit. Just let me know. And anyway, as for today, we're coming to the end of this class. The City College semester is nearly over. So I'm going to do malware behavior, Rust, which is actually in another class too, so some of you may already have seen it, and then the attack matrix. I just wrote a new project today for my Hack the Bay operational technology class, and I thought it was interesting enough to throw it in here. So that's the plan for today. And let's start with malware behavior. All right. So we'll talk about downloaders and launchers. Oh, good. Sure. All right, so downloaders are malware, which is staged malware, which, by the way, is one of the more common interpreter payloads in Metasploit. So you download a little piece of malware, and when it runs, it downloads more malware. This is often the case. So your initial exploitation is small, just so it's less suspicious, so it downloads faster, or because you have an exploit that only lets you inject a certain amount of code. So you'll put a small thing, and then it'll download something else. So it'll typically use Windows API calls. Like I say, a normal developer that just wants to get the job done, they would use these high-level API calls like URL download to file, followed by winexec. That would be the simplest way to do it. The native API, you could do it with raw sockets, but that would be much more painful. So that's a downloader that downloads more malware. Then there's launchers that prepare another piece of malware for execution. Now, often they have the malware hidden in like a resource section. So it's loaded as if it was just an image or other incidental data, and then they load it into RAM and execute it. This is actually quite effective at bypassing antivirus. I've written code that does that. All right. And then backdoors, of course, are something that give you persistent access to the machine. The simplest one just creates a new account with a username and password you know. Other ones start listening on a certain port or making outward connections and so on. And typically they try to conceal their network traffic by making it look like DNS or HTTP traffic so that your network scanning devices won't detect it. And once they're on there, they give you control of the machine so they can manipulate the registry, create directories, search files, etc. Reverse shell is typically what you want on a Windows machine because Windows machines have an active firewall that blocks incoming connections and does not limit any outgoing traffic. That's normally the case because you want to be able to go out and connect to file shares and servers and internet anywhere, but you don't want to provide any service because you're a client. So if anybody sends a request to like access your file shares or anything, that's typically blocked. So therefore you cannot connect from the outside to a strange listening process. What you have to do is the internal infected machine has to reach out to the command and control center, and that's called a reverse shell. And you can do it with just a couple of command line commands, but there's lots of malware that will do it. And this is the most common way it works because it punches through the Windows firewall. It's the most common way to infect a machine. So you can do it, if you make your own shellcode that does this, or you download a commercial or a common shellcode, what it does is called create process and create a socket to the remote machine. A socket is a network connection for two-way communication consisting of an IP address and a port on your end and an IP address and a port on the server's end. So now you have a channel for two-way communication. All right, and then you run command cmd.exe, and then you tie the input, output, and error to that network. So now you accept commands over the network, which are executed as if they've been typed in, and the response goes out over the network. You can make it multi-threaded. That'd be nice, one thread for standard in, one thread for standard out. Otherwise, you need two connections, one for traffic one way and one for traffic the other way. And remote administration tools are these executable programs. There have been tons of them. There's I read about them all the time in the threat intelligence. People always have new ones. This is typically what you do. You hack a machine, you get some ability to inject code, then you put on one of the standard RATs that just gives you a whole lot of remote control capabilities. And of course, these are not necessarily malicious. There's a whole bunch of standard remote control tools used by real network administrators for legitimate purposes, and most of them can be considered like dual use. They could be used for a legitimate purpose, or they could be used by a bad actor to control your machine. Poison ivy is a old rat from the Windows XP days. There's new ones. All right, and once you compromise a bunch of these hosts, you then have a botnet, a bunch of machines under your control, and you can then use that botnet army to do something like launch a DDoS attack on somebody. So the botnet has many hosts. Rats typically control fewer hosts, and rats typically control victims one by one. That's why they're used by normal legitimate administrators, but a botnet issues commands that then go to many machines, and they all just follow the same orders. All right, so credential stealers are getting really big. I see them all the time in the threat reports saying what the current attacks are. They're getting very good, so they can infect your machine with one of these and steal all your cryptocurrency passwords, your network authentication passwords, your API keys, and all sorts of good stuff. And then, of course, they can log keystrokes too, and then they can get in all those cloud accounts. And this is very valuable. That's why a lot of people come in with legitimate credentials these days, because it's so easy to steal them. And often they can just buy them from other people on the dark net, people that have deployed these stealers, stolen a lot of credentials, and then rather than continuing the attack, they just sell the credentials. This is specialization in the underground. Another thing is people learn how to steal credit card numbers, and typically they just sell them. It's a separate criminal enterprise to use the credit card numbers to buy something and somehow launder the money. And they typically just pass it off to someone else, just like a burglar. They steal stuff out of your house, and they typically don't sell it themselves. They go to a fence who will sell it, someone who specializes in that. Now, in Windows XP, there was a thing called GINA that was used to authenticate in unusual ways like RFID and smart cards, and it was possible to intercept GINA calls and steal the credentials. So there was a GINA registry key that would have third-party DILs loaded for something like hardware, and so you could add an extra item here, so all the login traffic passes through a malicious library on the way to GINA to authenticate, and so you can steal the credentials there. So it has to do what we did in the project. It has to be a intercepting DIL, so it has to imitate all the functions of the real DIL, and so that's the game. And so most exports would call the functions, and you'll see it here. So here it is calling the MS-GINA function. All right, and at step 2, it logs it to a file. So it steals, this is a sort of keylogger that steals credentials and logs them to a file someplace for later exfiltration. But GINA is no longer used in modern versions of Windows. It's been replaced by something called credential providers. But there are some weaknesses in credential providers, and there was a rootkit on Windows 7. But like I say, unfortunately, this class doesn't contain modern Windows rootkits because they're very hard to make now, and I haven't found any good ones to put in the projects that work in any understandable way yet. So I will when I find across them. But Microsoft's defenses have kind of killed off the previous generation of rootkits. Now, hash dumping is still a popular activity, though. Once you get the ability to execute code on a machine, if you can escalate to system privileges, which is pretty easy to do, then you can dump the stored password hashes, and they look like this. For every account, you have an LM hash, which is no longer used. It just contains this dummy value. But the NT hash contains information about your password, and you can see it's repeated. Like these two accounts have the same hash. A bunch of these have the same hash. Microsoft hashes are not salted. So if two users have the same password, they have exactly the same hash. And it's weak in many other ways. It is literally 1 million times weaker than Linux password hashes. So stealing these hashes and then cracking them is very common, because it's quite likely you'll be successful at cracking Windows password hashes. You can often crack them just by Googling for them, because Microsoft has never updated their hashing system since 1993, and people have just dumped information on the internet about all those hashes, so it's ridiculously easy to crack these hashes. They're still a little bit better than just storing plain text passwords, but not really a whole lot better on Windows systems. All right, so like I say, that's what's here. And there are toolkits to steal the password hashes, and there are toolkits to pass the hash, because in Windows domains, you can authenticate to servers by just sending the hash value without cracking it. A very strange thing about the Microsoft system. So if you steal the hash, that might be all you need. You don't even need to crack it. You can use it to authenticate to the next server and do lateral movement through the network, even though you don't actually retrieve the password behind the hash. So to steal the hash, you have to get a high-privileged process above the administrator to do it. So you typically inject a DIL into the local security authority subsystem service, which is managing authentication and therefore has access to the hashes. That's a common technique. There are other ones. This pwdump tool does it that way. Injects a DIL into a malicious DIL into LSASS, and then it can call get hash in order to get the hashes out of the security account manager. There's a pwdump variant that uses different libraries to access the security account manager, and it has various functions here, SAM get private data, and a couple of Microsoft system functions with not very obvious names to decrypt it. These are all undocumented. This is stuff Microsoft doesn't want normal software developers doing, of course. There is no reason for a normal software developer to have access to the system hashes. All they should have access to is like information from the OS about whether someone's logged in or something, but they shouldn't actually see the hash. So these are all, like the native API, undocumented functions that hackers have figured out how to use, but Microsoft didn't really want them using it. And so here's some API calls used by a pwdump variant. Here it is calling samserve.dil and advanced API 32.dil. And then here's those system functions 25 and 27, as it's going to decrypt the hash. Microsoft hash passwords are hashed with one round of MD4, and then they are encrypted with reversible encryption with the key hidden sort of in the registry. So that is just sort of pointless, but that's why you do need to go through a decryption operation to get them. And so the pass the hash toolkit also injects a DIL into LSASS. And it'll use different API functions, but it'll capture the hash as it's being sent around through the system. So let's try a Kahoot. It's 11A, and I should have Kahoots somewhere. Here they are, 11A. Good. All right. Small simultaneous population today. Oh, what's the last digit? Oh, thanks for telling me you can't see it there. It's a 1. Good. All right. Well, I imagine that's all that are coming. All right, so what's poison ivy? What kind of malware? Yep, it's your remote access tool. All right. Okay, which one of these stores malware in the resource section? That's a launcher. A downloader, of course, goes to the internet to get the next bit of malware. But the launcher has it stored as data within the original file. All right, which one causes the infected machine to send a SYN to the attacker? That's a reverse shell. It makes an outgoing network connection, SYN, SYNAC, ACK, to the command and control server. All right, which technique is no longer possible in Windows? Gina is out of date, not used in modern versions of Windows. All right. And which one injects a DIL into LSASS? More than one of these. pwdump and pass to hash both do that. All right. All right. Anyway. Oops. So, keylogging, we've been playing with these for quite a while in the projects. Kernel-based keyloggers would be hard to detect and would be part of a rootkit, but that's not that common. The user-based keyloggers use the API, and then they either hook or poll. If you hook, then what you do is you connect to a system call, an API call, so every time there's a call, it will also call some extra code. And polling is where you just constantly check to see if a key is up or down, and notice when it makes a transition. So get async key state will identify whether it's pressed or unpressed, and then you can get the name of the window, because if you just get key presses, that's incomplete information. On modern machines where there are many windows, you'd also like to know which window was open when the key was pressed. So you want to get both of them, and you'll have to be looping through these frequently enough to catch all the keystrokes. So this is the get foreground window. If it's a new window, log that now we switch somewhere in a new window, then call get async key state. Are done iterating through all the keys, check next key, and you just go through a loop, check and see what keys are pressed. That's the sort of flow chart you'd have for that kind of, for a polling keylogger. And so if you just do strings, you'll see things like this: up, down, numlock, right, shift, that sort of thing. That's a pretty easy way to spot it. Unless they choose to encode this information in a non-obvious way, it'll be pretty obvious it's a keylogger recording the state of keys. All right, and then there's persistence mechanisms. These are ways to stay in control of a machine even when it reboots, even when they close the browser window and so on. So the most common thing is to use a run key, like the malware we've been playing with in the earlier projects had, where it automatically launches every time you restart. You can also put it in various DILs and libraries, things that automatically launch. You can Trojanize binaries, and you can do DIL load order hijacking. We'll go through these. So the most common one is the run key, of course. That automatically runs every time you restart the machine, and auto runs will show a lot of others. There are a lot of ways to make things automatically launch in Windows. And you'll see Process Monitor making these registry modifications when you run malware on a test machine. So that can detect all of these because they all involve making registry writes, like you see here, registry open key, registry close key. You see what registry operations are done in Process Monitor. And so that's one way to find out if malware is modifying the registry for persistence. App init DILs are loaded into every process that loads user32.dil. And I suppose the idea is if you have something like a special keyboard or something, then anything that interacts with the user would want to have access to those library functions, so you'd want this. So there's a registry key that has a list of DILs that'll load into many processes. And so that's a way to get malware to run. And so beginning with Windows Vista, however, again, they're disabled by default. They do support code signing, but now supposedly the whole thing is disabled when Secure Boot is enabled, but Secure Boot is often disabled for various reasons. So it's not clear how many machines would still be vulnerable to this. Certainly some, and perhaps a lot. WinLogon Notify is another DIL that handles Windows logon events. So if you can get in that list and add a DIL to that, then you're not going to steal ordinary passwords tied into email and stuff, but you are going to get login passwords, and that might be all you want. All right, SVC host DILs is the main one used to run all the services. We've seen it in Process Explorer. There's usually like 10 or 15 SVC host processes running, and each of them is hosting 5 or 10 background services. So they're all defined in the registry, all the services. And so you see them in Process Explorer. All these pink ones are SVC host, and each one of them is hosting a whole bunch of Windows services, like you see here, system and server and themes and user profile service and so on. This is how all the background stuff runs, mostly, is with SVC host. And you can easily just add yourself to one of these groups. The SVC host in the registry just has a container for each one of these. And if you go into and each one of them just has a list of things to launch. So your malware can just add itself to those lists, and then it will automatically launch before you log in as a background service. So that's the parameters of the service DIL value in there. Yep, and you'll just have a path. So this is going to launch something called app-host-svc.dil and so on. So you can just add yourself to there. And you add it to an existing group, or you could overwrite a service that doesn't matter because there's hundreds of things running on Windows machines that nobody ever actually uses very often, so you could break them and nobody would usually notice or care. All right, so those are both good ways to do it. So if you want to detect it, you can monitor the registry. Just watching for unauthorized registry changes is one way to detect this sort of attack. All right, let's try another Kahoot. 11B. All right, so which one is a keyboard driver? That would be in the kernel. The drivers are in the kernel, so that would be one way to make a keylogger that runs in kernel space. All right, which one uses get async key state? That's polling. Getting the immediate state of the key means you're going to have to keep coming back frequently to tell when that key is up and when it's down. All right, which of these depend upon registry manipulation? Yeah, they all do. It's all controlled through the registry. All right. All right, which tool records registry modifications? Prop 1, we've used it in the projects. Yep. All right. All right, so which item is loaded into every process with user 32? That's AppInit DILs, which are somewhat more limited now. I'm not sure how much they're relevant in modern versions of Windows, but that's what they did. All right. I need to wait for this. I know who they are. There's only 2 competitors. All right. So then you could also Trojanize a system binary, and we've done this in the projects where you actually take an executable and you modify the code. That's, of course, one way to do it. You can put it in a library. One thing you might want to do is attack the entry function, so as soon as the DIL is loaded, the malicious activity will take place instead of waiting for some function to be called. And so what you do, you find an empty portion of the binary and insert some code and then jump to that. And you typically want to preserve the normal function of the DIL so you don't break anything, but you add some extra functionality. So here, for example, the original code might look like this. It's going to prepare the stack frame and then start putting variables on the frame. And the Trojanized code is going to jump somewhere else. Rather than doing any of this, it's going to jump to some other location, do some unauthorized things, and then presumably jump back here to continue doing the normal thing. You can do search order hijacking. This is a nasty trick, but the fact is when you load a DIL on Windows and you don't specify the entire path to the DIL, it'll first look in the directory from which it loaded, then the current directory it's working in, then the system directory, then the 16-bit system directory, then the Windows directory, then it'll go through the path environment variable. And what that means is if I get you to download something and unzip it, for example, and the unzipped thing contains an executable, but it also contains a DIL, which you probably won't notice, then when your application tries to load a legitimate Windows DIL, it'll first look in that directory and get the malicious DIL that I put there with the same name. So that's a simple way to trick an application into loading a false DIL, and they call that load order hijacking. So there's also, to prevent this, there is a known DILs registry key, and that overrides the search order. So this protects certain system DILs from being spoofed by being in the wrong directory. It stores the right directory they should be in, and that prevents that. All right, it can only be used, so you can only do it elsewhere, and that's they're not protected by known DILs. It's a good sounding security measure, but not all DILs are protected that way. So Explorer.exe lives in Windows, loads this from System32. It's not a known DIL, so the default search is performed, and a malicious entry in the Windows directory will be loaded instead. All right. And we've done that in the projects. We took over a sysinternals tool, BGInfo, this way. All right, it turns out there's a lot of vulnerable DILs in there. There are tools to search for them. This is probably information from an older version of Windows like Vista or so, but it had 50 vulnerable DILs, and as we found them, they're still out there for some software still has them. And so there's a tool from SANS that will scan, searching for DILs. It would seem like a pretty good idea. You look for DILs that have multiple times different files with the same name, and one of them's not signed. That would be a pretty good clue that this is happening. Although not everything in the Windows operating system is signed. It probably should be, but it isn't. And then there's the big issue of privilege escalation. Once you are on a system, if you're not the administrator, how do you rise to administrator? If you are the administrator, how do you rise to system? And both of those, there are a lot of standard tricks that work. There's ones built into Metasploit. The same trick just seems to work for generations of Windows. Microsoft does not seem to care. It's surprising how long those things work. You would think that once it gets built into a public tool, Microsoft would patch it in a hurry, but that doesn't seem to happen. So it's often done with DIL load order hijacking. So processes run by the user can't do everything. Sometimes you require administrator privileges, and sometimes you require system privileges above administrator. So the SE debug privilege was intended for debugging. If you can get that privilege, then you can do a lot of, then have one way to escalate to system privileges. So here's how malware did it. You would call token adjust privileges, open the process token, look up the privilege value for SE debug privilege, and then write it into the token. So there are API calls for all this to just raise your token, raise your privilege. And apparently you can execute them with just administrative privileges, so it's a pretty ordinary process. All right, and then of course, you want to cover your tracks. User mode rootkits, which is the modern kind that certainly exist. They modify the internal functionality of the operating system, but without going into the kernel. So they're less powerful, but they can do quite a lot. And so it might affect the import address table hooking for an individual portable executable. So you could modify, say, cmd.exe, and then anybody running command line commands that did a directory would not be able to see the whole directory because you hook the function calls from inside there. That's one way to do it. And it looks like this. You have a legitimate program here, which is going to call terminate process, but it goes to its import address table to find the create process, and with the hook, it's going to have malicious number here. The real functions are all at 7C, but the fake one is here at 34, so the hook will go to the wrong kit. This is a user mode rootkit. That's how they all work. All right. And then the alternative is inline hooking, like we said, where you actually just modify the executable code in the function. This requires more skill, it's more likely to break things, but it's more subtle. You don't just put it right in the addresses where it's pretty easy to spot. You actually modify the assembly code, the machine code of the function, and that's going to be really hard for anybody to detect. About the only thing they could do is detect that the MD5 hash has changed, but then they wouldn't really know if that came from Windows Update or what. So the tool, Tripwire, can do this. Tripwire can watch to see if any system files change. The problem is you have a big background of things that are changed by normal processes. So it's not as easy as you might think. Anyway, let's take a look at the last Kahoot. All right. I've had some Tripwire projects in the class and they weren't much fun. Install Tripwire, it was hard to configure, and then it gave you a lot of messages even when nothing bad was happening. That's a problem with all defensive tools. They typically flood your analysts with a lot of false positives, and that's very counterproductive. All right, so which item puts malware in an empty portion of a Windows component? That's where you actually modify a system binary. Possibly the most powerful technique, but the most difficult. All right, which registry key prevents load order hijacking? Yeah, known dills. It occurs to me, what I said is if you included the whole path, you wouldn't have this problem, but I think the way code works, you don't get a chance to include the path. You just have like an include function in in your C++ code, and you don't get a chance to put the path there. So you're really dependent on the operating system to find it, but the known dills have recorded where that dill lives, so the system doesn't have to hunt for it. It knows the right place to go get it. All right, which one of these has 50 vulnerable dills? Explorer, the process that draws the desktop. A really important process. All right, what hacking tool can do privilege escalation? Metasploit. Do it all the time in the hacking classes. All right, and which one changes function code, not pointers? That's inline hooking, where you modify the code. All right. I think I know who the winners are already. All right. All right, let me stop this recording.